So we ended our discussion last time by discussing how quantum states and physical apparatus, such as the Z apparatus, can be represented as mathematical objects. And in particular, we claimed that perhaps the quantum states can be represented as vectors, or more precisely as probability vectors, and the physical devices which bring about a change in those quantum states can be represented as matrices. So let's make this idea a little bit more precise and do the actual math behind this. So if you recall the quantum experiment that we've been working with, let's say I have an initial state which is an up arrow along the z direction, and we have an apparatus which is also oriented along the z direction, which we call the z apparatus. If I pass this state, an up arrow, through the z apparatus, what comes out is still the up arrow. Likewise, if I pass a down arrow through the z apparatus, what comes out is another down arrow. However, if I have any other state that I start with, at the output of the z apparatus, I would still observe either an up arrow or a down arrow. So in other words, the z apparatus somehow only outputs an up arrow or a down arrow state. Probabilistically, this suggests that these two events, observing an up arrow or observing a down arrow through the z apparatus, are somehow mutually exclusive events. At the same time, since every other state maps into either an up arrow or a down arrow at the output of the z apparatus, perhaps this suggests that these two states, at least in terms of a vector space, can be thought of as constituting an orthogonal basis, a linearly independent orthogonal basis based on which we can construct a two-dimensional vector space. It turns out very surprisingly that this is all the math that we need to completely explain all the observations of the quantum experiment. That is, a two-dimensional vector space suffices. For instance, one way we can represent the up arrow and the down arrow as basis for the two-dimensional vector space is to use a column vector, a 2x1 column vector. And for instance, on this slide, I've represented the up arrow as a column vector which has the first entry as 1 and the second entry as 0. Likewise, the down arrow as a column vector with first entry 0 and the second entry 1. And as a shorthand and commonly seen notation, I've also represented the up arrow enclosed it within what are called kets, which is a vertical line followed by the state and then an angular bracket. So I've represented it with a +1 and an up arrow with a +1 and a down arrow with a -1. And this is again a notation you might encounter in your studies. Nevertheless, it turns out that these two, even though they may not appear to be orthogonal to each other, at least if I'm just making an up arrow and a down arrow in physical space, it turns out that these two are actually orthogonal to each other when viewed in somewhat different representation. And we'll talk about a Mobius sphere kind of a representation for these states. And if you want to know a little bit more about the Mobius sphere, I'll refer you to our series of videos on complex numbers. However, these two states, the way I've represented them as column vectors, you can check for yourself that the dot product of these two turns out to be 0. And in that sense, these two states are orthogonal to each other. Now, with these two as our choice for the basis, I can now represent the z apparatus as a matrix, in particular as a 2x2 matrix, in the form that we've written on the slide. That is, z hat as a 2x2 matrix, or rather a 2x2 diagonal matrix with entries 1 and -1 on the diagonal and zeros on the off diagonal. And the reason for this choice of representation of the z apparatus is because we saw in the quantum experiment that the up and the down arrow states go through the z apparatus unchanged. And in that sense, at least physically, what that hints at is that these two states are eigenvectors of the matrix representing the z apparatus. Because by definition, when a matrix acts on its own eigenvector, the output is the eigenvector multiplied by some multiplicative constant. So the eigenvector comes out of that transformation unchanged except for some scaling factor. And this is what we saw physically in the, or rather at least in the thought experiment that we have done. So let's check this idea that indeed, if I represent the z apparatus using the z hat matrix here, are the up and down arrows in the way that we've represented here indeed the eigenvectors or eigenstates of this z apparatus? So here we have the z hat matrix, which we've written in the basis where the plus arrow or the up arrow is represented by the column vector 1 0 and the down arrow is represented by the column vector 0 1. So in that basis we are claiming that the z apparatus can be written as a 2 by 2 diagonal matrix with entries 1 and minus 1 on the diagonal and zeros in the off diagonal. Now if I take this z hat matrix and multiply it by the up arrow column vector, which is 1 0, I end up getting the up arrow again, and the multiplicative constant is just plus 1. Likewise, if I take the z hat matrix and multiply it by the column vector 0 1, which represents the down arrow, I again get back the down arrow, except that I pick up a multiplicative constant minus 1. Therefore, the up and the down arrow states are indeed eigenvectors of the z hat matrix. And this mathematically captures the idea that when an up arrow passes through the z apparatus, it comes out of it unchanged, it remains an up arrow, and the down arrow, when it passes through the z apparatus, it comes out of it unchanged, it remains a down arrow. So given that we have made a choice for a basis for the two-dimensional vector space, we can write an arbitrary quantum state as a superposition of those two basis vectors. For instance, I can write a quantum state psi as C1, some constant, times, or rather scaling the up arrow plus another constant C2, which is scaling or is the coefficient of the other basis vector, which is the down arrow. And this is all we require to explain all the observations of the quantum experiment, which might seem very surprising since the experiment talked about a lot of things, but we've just boiled it down into a two-dimensional vector space. Now, if this is indeed a quantum state, and if you recall the discussion on how we talked about extracting probabilities from the coefficients of vectors, when we write, let's say, a general vector as a superposition of the basis vectors, the basis vectors are multiplied by some coefficients. And we motivated this idea that if I take these coefficients and square them, or take their modulus and square them, somehow we can use this sort of idea to define a probability. And I'll refer you to the video where we talked about this at length. Now, if this is true, then what we can claim, or what we want this vector psi to represent, is that given a general quantum state such as psi, the probability for us to observe an up arrow when I pass this state through the z apparatus is modulus of c1 square, and the probability of observing a down arrow when I pass this state through the z apparatus is modulus of c2 square. And this is sort of our way of constructing a quantum state with probabilistic interpretations which help explain the observations from a physical experiment, in our case a thought experiment. But if there were an experiment which were to produce such results, this is one way that we can think of representing quantum states, associating probabilities with those coefficients, so that we are able to explain the outcomes of this experiment. And we're going to play around with this to see if indeed this is true, if indeed this is able to explain all our observations. Now, if this is true, one of the things that we can immediately construct or claim is that, let's say, the up arrow, I want to assign, upon measurement, I want to assign it a value of +1. Now remember that plus the up arrow is a vector, right? It's a quantum state in some ways, and upon measurement it'll give me some value. Think of this as a coin. We have two sides to the coin, a heads and a tails. I can ascribe a numerical value to the head and a numerical value to the tail. And this is also something we talked about in our video where we talked about probabilities and sort of the different interpretations of probabilities. So in the same way, let's say upon measurement of a quantum state which is in the up arrow, we want to assign a numerical value +1. And if it were a down arrow and we were to perform a measurement, we'll assign a numerical value of -1. And if this is true, and the probabilities of observing a +1 is modulus of C1 square and probability of observing a -1 is mod C2 square, then the expectation value of what we observe or what we expect to observe would be modulus of C1 square, which is the probability, times +1 plus modulus of C2 square times the actual outcome that you observe, which is -1. And so the expectation value, if I were to pass many such quantum states all prepared in the state psi through the Z apparatus, our expectation value would be simply mod of C1 square minus mod of C2 square. And again, I'll refer you to the video where we did define what the expectation value is, what the variances are, which we'll use in the next part of the video. Now, if we use a simpler representation and perhaps describe the up arrow as a +1 state and the -1 state as the down arrow, and we've been using this as the basis for our two-dimensional vector space, and our claim is that we can describe the entire quantum experiment just using this two-dimensional vector space. In this representation, a right arrow, which is also something we used in our simulations, a right arrow which gave us a 50% chance of observing an up arrow when we pass the right arrow through the Z apparatus, and a 50% chance of observing a down arrow when we pass this through the Z apparatus, can be represented as 1 over square root 2, which is the coefficient multiplying the up arrow state, and 1 over square root 2, which is the coefficient multiplying the down arrow state. And the reason this could be a representation for the right arrow is because the probabilities give us the right answer. So, for instance, 1 by root 2 square is just half, and what this expression of the state which represents the right arrow tells me is that, okay, there is half a probability that I'll observe a +1 state, which is the up arrow state, and there is a 50% or a half probability of observing a down arrow state, which is the -1 state. Now, I do want to distinguish between the right and the left arrow as well. So a simple way I can define or describe the left arrow state is that instead of a +1 by root 2 multiplying the -1 state, I can use -1 over root 2 multiplying the -1 state. Now notice, this doesn't alter the probabilities, because to get the probability from the coefficients which are multiplying the basis of vectors, I have to square those coefficients. So the left arrow state also has a 50% chance of giving me a +1 or a up arrow state, and the 50% chance of giving me a -1 or a down arrow state. Now, given these two probabilities, I can again calculate the expectation value, or if I pass many such states all prepared along the right arrow direction, and if I were to pass many such states through the Z apparatus, what is the mean value that we expect? That's the expectation value. Now, I expect to see a +1 numerical outcome with a probability of half, and a -1 numerical outcome with a probability of half, and therefore the expectation value for the right arrow state is just 0. Similarly, the expectation value from the left arrow state is just 0. Now, what about the expectation value of the eigenstates? Which means if I already have a state prepared with an arrow pointing up, which we can denote as a +1 state, or an arrow pointing down, which we can denote with a -1 state, and we pass it through the Z apparatus, what do you expect to see? Well, we just expect to see +1 for the state that with an arrow pointing up, and -1 with the state with an arrow pointing down. And that's what the math tells us. But the more interesting part is calculating the variances of these different states. And I encourage you to watch the video on probability, introduction to probability, the mean and the variance, and how do you actually compute it. So if I were to compute the variance for states such as the eigenstates +1 and -1, and what this really means is that if I have many such states let's say +1 states, and I pass them through the Stern-Gerlach apparatus and see the outcome, measure what we observe at the outcome, and we find out the variance in the data. Of course, we'll find that for these states, since nothing really changes, the variance will be 0, which means these are the analogs of what we can call Shor variables, or in this particular case, we can just call them Shor states. The way you compute the variance in this case is that you take the value that you observe at the output. So for the arrow pointing up, what you'll observe at the output is a value +1. You square that value and multiply it with the probability with which you observe that value. Likewise for all the other values that you're likely to observe. Now for the +1 state, the only value that we'll observe is a value of +1. So I square that, +1 squared, and multiply it with its probability, which is just 1. And from here, I subtract the square of the expectation value of that state. For the +1 state, just as we computed in the previous bullet point, the expectation value is also +1. So if we take the difference of the two, we find that the value is 0. Likewise, the variance for the -1 state will also be 0. But here is the interesting part. If you were to calculate and do this calculation again for states which were initially pointing along the right direction, right x-axis, positive x-axis, or negative x-axis, we will find that the variance is 1, so it's no longer 0. And this tells us that somehow these states have an uncertainty with regards to the outcome that we'll expect to see. And these states we can call as analogs of random variables, so I've just written them down as random states. This variance in what we observe at the outcome lies at the heart of the uncertainty principle. In fact, the uncertainty principle is the relationship between the variances of two pairs of variables or two pairs of observables, as we'll see in the next video.